Welcome back, students. Today we're continuing to working with quadratic functions. It's just this time we are going to be modeling situations using quadratics. So normally what happens is data is collected, you plot those data points, and if you start to see that U-shaped curve, a quadratic would probably be a good fit for that data. So what we're going to do today is the formula or the function, the equation will already be provided for you. It's going to be a lot like class where you're going to graph that, you're going to analyze that graph, but then you're going to use that graph to then answer some questions about the situation. All right, so a first example says a tennis player hits a ball upward with an initial velocity of 48 feet per second. The function h of t equals negative 2t squared plus 7t plus 4 describes the relationship between the height in feet of the tennis ball and the time t in seconds of its time in the air. All right, so main thing that I need to do there is one, yes, now there's a background, there's a story behind it. So I can picture playing tennis and hitting this ball back and forth. Time's going to pass, and that ball with relationship to time is going to be a certain height in the air. All right, so first thing that you should do is you should take this quadratic and type it into your graphing calculator, or I suggest that you use Desmos. So notice I didn't write the h of t equals, and then what I did is I replaced my x's, my domain, my input with, or I replaced the t's with x's just to make it a little bit more standard. Then I can think about these being along the x-axis. And then I didn't even put the equals to, because you don't even need that when it comes to Desmos. So notice, okay, because I can identify my a is negative 2, my b is 7, and my c is 4. Because that a, that coefficient, that leading coefficient is negative, that means that this graph opens down. Because think about it. If you hit a ball up in the air, think about the curvature of that ball. It goes up, and then it's going to come back down. So you can use the formula h equals opposite b over 2a in order to come up with where that x-coordinate of the vertex is, or you can click and drag, click on the parabola itself, and then Desmos automatically tells you where the vertex is located. That is the center of your graph. So when you make your table of values, okay, make sure that you include your vertex. Put it in the center when you are making your graph. Oops, wrong thing. And then you are going to then count up, and you are going to count down. So 1.75 is in between the whole numbers 1 and 2. So 1, 2, 3, 4, and then 4, 3, 2, 1, 0, negative 1. So remember that you will find those by converting that to a table and get those off the graph, and then you will make a graph. So I'm going to pause the video and do all of that. All right, so I got all of these points off of my table. I plotted those points. I adjusted my x-axis and my y-axis accordingly so I could plot these points. And notice that this time I also labeled my x-axis is representing my time. My y-axis is representing the height. And then I plotted these points. Now, before I connect those, there should be a couple other points I need to make sure that I have graphed, and my y-intercept is already up in that table. It's at 0, 4. And then also my x-intercepts. So one x-intercept can be found in the table because it has 4, 0. Anytime 0 is the y-coordinate, that means it's an x-intercept. My other x-intercept I'll have to pull off of the graph. I can click on it, and it's at negative 0.5. So this is going to be at negative 0.5, 0, comma. All right, so that's the only other point that I need to include is at negative 1/2. There it's on the x-axis. And then the best that you can, connecting these with a U-shaped curve. All right. Now, not all of these points make sense because it's an application problem. Okay, now this graph, okay, is modeling this function. Okay, so this function does have a domain and it does have a range, but not all of it pertains to our situation. So we're going to do our domain and range off of what the domain and range of the graph is. So as I've told you before, the domain, you can go as far left and as far right as possible. There is no limit to those. So that's all real numbers, or in interval notation, negative infinity to positive infinity. The range, because the graph opens down, means that it goes down forever, so negative infinity, and then it comes up to reach its maximum point. So this has a maximum point at the vertex, and the y-coordinate of that maximum is at 10.5. 1.125. And since it's actually on that point, we're going to use a bracket to say it actually reaches that point. And then the axis of symmetry is the x-coordinate of the vertex, which would be at 1.75. All right, so not all of this graph, okay, like I said before, makes sense in terms of the application problem. Really, the only part that makes sense would be this part. Okay, when time is 0, that means when the ball is being hit. And then anything after that until you have the tennis ball that is back on the ground. All right, so that means the first quadrant. Okay, so the first quadrant is really where we're going to be looking for all of our answers. If we were looking at the graph, yes, we can analyze the graph like we did last time. I guess I could also put my x-intercepts. I can also extend this to have my solutions is negative 0.5, 4. All right, so really the new part is just being able to use the part that applies to the scenario in answering questions about it. So it says, how long after the ball was hit does it reach its maximum height? So how long, that means that it's asking me for time. It's asking me for an x coordinate. When does it reach its maximum height? Well, that means it's asking about the vertex. So the maximum height, okay, that's the next question. The maximum height is 10.125. If I needed to, I would include my unit, which would be feet. A lot of times we'll just put how you're going to do it on homework is you're just going to type in the number, not include the unit. For this question, it says how long, so that means that we're talking about time, and this is being measured in seconds. So when did it reach its maximum height? What's that x-coordinate of the vertex? And that is 1.75, and that would be seconds. How long does it take for the ball to fall to the ground? Well, if it's on the ground, it means that its height is 0. So when is it back on the ground? And that would be in 4 seconds. Right, I have another problem like this that is already completed for us. And it's talking about football, so you can read through the scenario. And once again, the function will already be provided for you. You will then go to Desmos and you will graph that function. All right, so here is that function that has been graphed. Found my vertex. But this time, notice I did not just go one up and one down because these are a lot bigger. Going by ones would only give me about this portion of the graph. I want to see more than just that. All right, so you want to be able to see a good representation of that graph. So you're going to have to be comfortable with possibly changing the scale or possibly counting by more than just ones in your vertex. You want to try, if possible, to include those x-intercepts in your table. All right, so 48. Okay, all I did was I looked to see what would get me a good representation for that graph, and I decided that going and including these points, if I plotted these points, I would be able to see the basic curve of this graph. I include my vertex, okay, and then analyzing it, my domain is all real numbers, negative infinity to infinity. My range, since the graph opens down, it's talking about a football, it goes up in the air and comes back down. It's a very common type of a problem. It means it goes from negative infinity to positive 32. Where does it cross the y-axis? Where does it cross the x-axis? Those can be just pulled off of Desmos. The maximum value, the maximum height that the ball reaches is 32, and the axis of symmetry is at 48. So then, coming up and answering these questions, how many feet from the kicker does the ball reach its max or reach its highest point? So the ball was being kicked right here at time 0. Highest point's the vertex. It said how many feet from the kicker. And so that is going to be that x-coordinate because here it says relating the height of the ball to the feet from where it was kicked. So in this case, the x-axis is representing how far away it is from the kicker, and the y-axis representing the height of the ball. So this one was 48. It was asking for that x of the vertex. What is the maximum height of the ball? Well, that's 32. And then here's an interesting question. It says the goalpost crossbar is 10 feet above the ground. Does the kicker make the field goal? All right, so when the ball is 90 feet away, okay, because we need to do a little bit of math here, because it says up here in the problem that from the center of the 20-yard line, which is a 60-foot line, that this kicker is attempting to make the field goal. The posts are 90 feet away. So 90 feet away, what we would do is we'd figure out when x is 90. So we could go to Desmos, we could look at our graph. When we're at 90, what is the height? That told me it's 7.5. And since it says the crossbar is 10 feet in the air, it means that the football would need to be more than 10 feet up in the air if it's going to have a chance to make it above this goalpost. So this would be a no. All right, so a lot of the same today, basically just taking the equation given to you, typing it into Desmos, analyzing it, but then going one step further, and that's to be answering these questions here. Like what happened on this, do not be afraid to not count by ones. Okay, you need to make sure that you have a good representation if you're to plot those points, what your graph is going to be.